from 10 to 10:35, 40, something like that. So you can come today or Friday, right? Or next Monday, so whenever you want to come. Right? All right? So, you didn't ask the class average.
What is it?
It is typical to have about 65 to 70 for this class because if you see the national average, it is about 50, a little bit below 50. So that's the reason why this is considered as the harder course. Okay? So you're going to see the class average. So with that, this is the one.
I might need your.
You can see over
You're staying
here.
here till 5, right? I might need your help with the post lab because I'm missing. Oh, I could take
About
help you
50%, right?
Intel lab. Intel
So
lab.
this is based on how many? You have 33 universities, including UT Austin, A&M College Station, right? And about how much? About 3,000 students. That's the average of that. It's about 50. Right? So you gonna have a little bit more time for this course. So make sure you study daily, you review the content, right? That's gonna help. That's the reason why you have SI leader for this course, right? All the way back over there. You have tutoring service, you have office hour, of course you have class, right? So make sure you don't skip any class. Attend regularly, they're gonna help a lot. And then attend SI sessions. You can have a tutoring service, you have info in the syllabus, right? So you can have help from all different sides. Okay? Alright. So now we're gonna start new chapter, chapter 5. So chapter 6, you're gonna have reactions again. We're gonna go there. But chapter 5 gonna be kind of qualitative. You can think this as a review of Gen Chem 2, if you like, right? Kinetics, thermodynamics. You had a lot of equations over there, right? So we're gonna see some of the equations from that, but you will not do any math over here. Okay, so you will not derive the equation. Probably you will not have the numerical questions for the exam. We're gonna review the meaning of that, application of that. Okay, so that's gonna be the qualitative rather than quantitative. Okay, so we're gonna do that. So of course, whenever you see the kinetics, thermodynamics, you have different parameters, free energy, enthalpy, entropy, of course, equilibrium constant that we reviewed already, right? So we're going to see the interrelation of these parameters, and then we're going to see the implication of that for the reaction. That's the point we're going to focus over here, okay? So with that, for chemical reaction, let's see the one we already saw the equation, okay? This is not new. If you see over here, this molecule in this particular conformation, okay? So this is the Newman projection of the molecule. What do you think? Which molecule this is gonna be? Can you name that? So for Newman projection, remember, you're gonna do carbon 1. This is the front, right? So this is gonna be carbon 1 over here, the front carbon. And then on that, you have one hydrogen over here. you're going to write H2. You have two hydrogens, this and this over there. And then you're going to have CH3, other one, right? This one. And then for the back carbon, let me write with a different color to make less confusion. So this is labeling C1 and then C2. Okay, just the labeling, two carbons. And then you have the same thing. On the back, you have two hydrogens there. So the purple one, you have this and this. I'm going to write H2 for that. And then I have CH3. So I'm going to write something like this. So how many carbons? 1, 2, 3, 4. Butane. Right? That's the butane molecule. So you have different conformations there. Totally eclipse. And then you have the anti. And then you had the Gauss conformation, right? So which one is this of all the conformations you have? So anti, it is written over here, right? So why anti? For one carbon, you have CH3 over here, and the other carbon you have CH3 over there, and the opposite side. Okay? So this is anti. And of course, you're going to have the rotation along this. You're going to rotate along this direction over here between the central two carbons. Okay? So if you do that, of course, you can change from anti to Gauss or total eclipse, whatever you want to make, right? So this is Gauss 1, in which you have about 60 degrees between the plane of different atoms. Okay? So we know that anti is going to have the most stable structure, going to have the least energy for that. And then if you go to other conformation from there, it's going to cost energy. Right? So you're going to have the higher energy. That's why this is the energy that the molecule has to pay to go to the higher energy conformation. Okay? So in chemical language, we're going to call that energy as free energy. Gibbs free energy. That's the name for that. Right? So whenever you're going to compare energy of one reactant or one conformation of that to the other one, whatever you have the difference in energy, that is called the free energy change. Okay, delta G is the notation for that. Okay, so if you go to the other way, if you start from Gauss and then you're going to go to anti from there, then what's going to be the delta Z in this case? So you are going from a higher energy. So you're going to draw the graph, going to be something like that. So what you're doing is you are going from Gauss to anti, right? Something like that. Anti is going to have lower energy, so we're going to make that to lower than that of Gauss, right? If this is the case, then what is going to be the difference you have? That difference going to be delta G, you're going to have the same value, but you're going to have the minus there because you have the lower energy for the product you have, right? So that's the different way of drawing that. So now the question is, just by seeing that value, can you predict whether the reaction is going to be favorable or not favorable? Or in the same name as ZChem2, whether it's going to be spontaneous or non-spontaneous. Okay? So we can see that qualitatively. So you cannot say how much until you do the math, but from the sign you can predict which is going to be lower, which is going to be higher, or which is going to be favorable, which is going to be not favorable. Okay? So for that, you have this relation, if you're going to do math. So delta G equals minus RT ln KU. Okay, this is EQ. KEQ is going to be the same equilibrium constant that we saw before. Okay, so that's the ratio of the molar concentration of product over reactant. Right? If you have any coefficient on the balanced chemical reaction, that coefficient is gonna be raised to the concentration power. Right? So that's the ratio, so we can calculate if we know the equilibrium concentration for the reaction. Okay? So if you know that, so you're gonna have the temperature. So that's the temperature for the reaction system. Okay? So you're gonna measure the temperature. Make sure you're gonna put in Kelvin, not degree Celsius or Fahrenheit. Always you're gonna put in Kelvin whenever you deal with the gas laws and kinetics, thermodynamics, in all cases. And the R gonna be universal gas constant. Right? So the value of that gonna be known. Right? So now if you solve that, so you're gonna have some value of delta G. Okay? Sometimes you're gonna have the negative, sometimes you're gonna have the positive, depending on the KEQ. Whether you're gonna have the more product or whether you're gonna have less product. Based on that, you're gonna have the different sign. Okay? So based on that sign, you can predict that whether this is less than 0 or negative, that means negative, right? Whether this is less than 1, greater than 0, that's going to be positive, right? So based on that, you're going to see whether the reaction is favorable, if favorable, in which direction. Okay? So for the first one, if it is negative, so what is going to be the direction favorable? That is to the right. That means more product you're going to have. So this is going to have more product, right? On the other way, if the other one positive, then it's going to be favorable to the more reactant. So right going to be product, left going to be reactant. Whenever it goes, you're going to have more of that, right? If it goes to the right, you're going to have more product. Go to the left, you're going to have more reactant, right? So that's how we're going to find out just by seeing the sign of delta G. If you have negative, that is, reaction is favorable to give more product. If it is positive, reaction is not favorable to give the product. It doesn't want to go to the right? So one thing, if you see this sign with delta G, so like that, you have delta G to the power small circle there, right? We call naught for that, delta G naught, okay? So that means it is as the standard condition. So you have constrained some of the parameters in the reaction. So what are the parameters? You have pressure, you have concentration, you have temperature, right? You have a lot of different factors that are going to affect the reaction. So you're going to keep temperature to this value. We call it room temperature sometimes for that, okay? And then you have the 1 atm pressure. We constrain that value. And if you have the reaction in the solution phase, then you're going to have the 1 molar concentration. Right? So 1 molar concentration, 25 degrees Celsius, 1 atm pressure. So if you have constrained these parameters for particular reaction, then the value you got for delta G is indicated by the small circle. That's what it means. This is the shortcut hint for the conditions. Okay, we called standard state for that. Alright, so now once we know delta G, then we're going to go to the reaction rate. Okay, so how are you going to define the reaction rate? So as an example, for entire gas, we just saw that, right? So what's going to be delta G? So for that, you're going to have delta G value was something positive. Right, 0.9 kcal, something like that in the previous slide. You have the positive value there. Okay? So that is the comparison of the energy of the product with the energy of reactant. Okay, so now, whenever you see the reaction rate, it does not correspond to that. So the reaction rate has nothing to do with the energy difference between them. But indirectly, it implies that, but actually what does the reaction rate indicate is how fast your product can be formed from the reactant. Okay? So that is indicated like this one. So the reaction occurs 10 to the power 10 times per second. Right, so you have the conformation changing frequently. So you have that many rate you're going to have, right? But if you see the other one, let's say this one, this is the butane derivative of the same molecule. The only thing you are doing over here is you are just putting the double bond on the central carbon, right? So like this one, you're gonna have you don't have that. You have only one hydrogen there, right? So you have one hydrogen, and then you have CS3 in the other one, CS3, right? Something like that. Okay. So now you will rotate the carbon-carbon double bond along this. So qualitatively, do you think the rotation of this is going to be easier or rotation of this one? So you're going to have H, and you have CS3, and then you have CS3 over there, hydrogen, hydrogen. So this one, right? So this is butane, and then this is butene. You have double bond there. That's the only difference, okay? So you are doing this rotation around the central two carbons in both cases, right? So just by looking at the structure, what do you think? Which is going to be easier to rotate?
A single bond.
Butane, right? So if you have double bond, you have more constraint, you have a stronger bond there. You cannot break the double bond when you rotate it. So you're going to break the pi-pi overlap before you rotate it. That's not easy to do that, right? That's the reason why if you see the rate of the reaction, what is that? Almost zero, right? It's not, it is possible, but it's going to cost a lot of energy. Very hard. So that's the speed. So you're going to have the rate of reaction very, very slow, virtually zero for butene, but it is very fast for butane, right? If you see the energy difference, of course you're going to have value over there, product minus reactant. But here, whenever you see the reaction rate, you're going to see the speed, the rate of change, okay? The concentration over time. That's the thing we're going to use to describe the rate of the reaction. But delta G is different from that, okay? Doesn't matter how fast it goes, how slow it goes, sometimes you're going to have the same delta G value for two reactions. But they may have different speed to go there, okay? So you can see the diagram over here, the same thing. So you're gonna see this one for butane. So this one is for butane. Butane, right? And then this one is for butene. Okay? So this is like that. So you're gonna have this. And then this one is like this single bond. You have CS3, hydrogen, hydrogen, and then you have CS3, H, and H. Right? So, I'll see. So, all the points I explained can be summarized over here. If you see the energy difference delta G, so it's not that different. Okay, so both have positive value delta G. So one is about 0.9 kilocalorie, right? Other gonna be about 1.4 kilocalorie. So for butene, a little bit higher than butane, right? So delta G is comparable. So in both cases, what it is saying is that the product is not favorable because you have the delta G positive value. If it has negative value, then yes, you're gonna say product is favorable. You're gonna have more stable product, but not over here because delta G is positive. Okay. So now the reaction rate. So for that, you're gonna see this. How easy to cross the energy barrier. If it is easier, reaction is gonna be faster. You're gonna have more frequent conversion to the product, right? So you're gonna say the faster reaction rate for that. If you see the energy profile with very high peak over there, barrier, then it's not easy to cross that barrier. So reaction is gonna be too slow or not possible at all. Right? So now you see the difference between the reaction rate and the delta G. Okay? So now, in terms of concept, if you're gonna separate that, so all this thingy, the barrier thingy, you're gonna call that kinetics. Right? So reaction kinetics. They're gonna be about the speed of reaction. And the thingy over here, delta G, or just the comparison of reactant product, you're gonna call that thermodynamics. Right? So that's the difference. All those speed thingy, rate thingy, they're gonna be included in kinetics, reaction kinetics. And then all those, the absolute energy value difference, they're gonna go to reaction thermodynamics. Okay, so you have two separate parts to discuss that. So now, let's do a little bit about the kinetics. Okay, so Arrhenius equation. So probably you saw this in Chem 2, right? Kr equals AE to the power EA over RT. So you don't need to derive this equation. So you're going to see the meaning of that. Right? So what this equation says. So this one, Kr, this is going to be the rate constant. So K is the rate constant, R is for the reaction, that's the indication, right? Just to make less confusion about the equilibrium constant sometimes, and then K, right? So this Kr is not equilibrium constant. This is the rate constant, okay? So the concentration over time, that is the rate. You can refer to that, the speed of reaction, okay? And then A is also the constant, but it is the reaction dependent. Okay, so you're going to have the one constant for one reaction. Right? So this is called the frequency factor. Right? So the term frequency is going to indicate for the collision. So if you have the reactants, before you're going to give the product, you're going to have the collisions between the reactant molecules. They're going to help to break the bonds with atoms. So once you break a bond with collision, then you're going to make a bond to make the product. So the first thing is to break the bond between the atoms in the reactant, right? So collision is going to help that. Of course, if you heat, you're going to have the head energy going to be added over there. You're going to facilitate to have the proper collision with that. Catalyst, they're going to help, right? But collision is the one they're going to do, right? So now, not all collision going to give it. The collision in the right direction, that is called the proper collision. It's going to refer to that. So the frequency factor is the fraction of proper collision. So that's the one you're going to refer, right? And then the other going to be EA. So this is going to be energy of activation, right? So in the previous diagram, you had the energy profile like that, right? So the peak you have, that peak and the reactant, not the product, reactant, that's going to be EA. So the difference between the top of the barrier you have with the reactant energy, that's the energy of activation. Okay? So now, if you're going to correlate the height of the barrier with the reaction rate, and this is the one we're going to use. Okay? So how to know whether you're going to have very high barrier or not? Just by seeing the EA value. So higher the value of EA, more higher going to be the barrier, and the reaction going to be slow, right? If you have the less value of EA, that means you're going to have the small barrier for the reaction and rate going to be faster. So EA going to say directly about the rate of the reaction. Okay? So if you have less height, this, then it's going to be easy to cross, right? That means you can have faster reaction. Okay? So EA and temperature, sometimes they are vital for the reaction. So this is the ratio you have in the rate equation, EA over RT, right? So if you increase the temperature, then what's going to be the overall value for this term? If you have more in denominator, the result is going to be smaller value, right? You are dividing by the larger number from denominator. That means it's going to make the EA barrier lower. So sometimes if you heat the reaction, you're going to have more product. That's the reason why. So if you heat the reaction, you're going to make the barrier height less, and you're going to have the more and more fraction of molecules capable to cross the barrier, and then you're going to have the product with that. Right? So you can see from here, at this temperature, at higher temperature, even at higher temperature, you have the fraction of product increasing as you increase the temperature. Okay? So if you increase the temperature, reaction is going to be faster because rate is going to be increased. or the barrier height is going to be decreased because the temperature is in denominator with the energy of activation. Okay. So now transition state. So do you know what is that? Transition state. So it is the transition between reactant and the product. That's what it means. Right? That's the transition means. So the short-lived reactant product, or you can call complex for that. So some bonds are partially breaking, some are partially making, just the intermediate before you have the product. So that is transition state. So which point do you think it's gonna refer in the energy profile? So the top of the barrier, right? So this thingy over here, sometimes if you take the energy of that, sometimes it's going to be hard to calculate, you can predict that. So delta G and then something like that. That sign is going to be for the top of the barrier. That is for the transition point between reactant and the product. Okay? So this is the notation you're going to use. So this is transition state. Sometimes the quantity you have in the transition state, you're going to call that activation complex. This is a different name for the same thing, right? So sometimes just the complex, right? So this is the transition state, right? So now if you take the same reaction, so you're going to have the anti-butane over here, right? So you're going to convert that to the gauge for that. Then what's going to be the position for the transition state? So you're going to have this carbon. So you're going to have CH3 over there. You have hydrogen, right? CH3 over here. And then hydrogen, right? So you are rotating that. So which one is going to be the transition point? Can you see can you visualize the conformation for the transition state? Remember you have this and this angle. So this angle, it was 60 degree when you have the anti. Okay? So gauge gonna be still you have 60 degree. So what you are doing is you are moving that CH3 over here. So before it was over here, CH3, you're gonna rotate that by this angle. So you go 60 degree and then 60. So you rotated 120 degree to have the gauge. Okay? So now, what's going to be the conformation when you do just 60 degree before doing 120 degree? So this is going to come right over here. Right? So CH3 and hydrogen are going to be in one plane. What is that? Eclipse. That's the transition state. You are going to have crowded, that's why you're going to have the high energy for that conformation. Okay? So that, to cross that point is harder. Once it crosses that, then it's going to go to 60 degree away from there. That's going to be gauge. Right? So that is called the transition state. So this is near eclipse. Right? So this is eclipse conformation. So that's how the reaction is going to happen. So it doesn't mean that you're going to have the rotational bond in every reaction. So for other reaction, you're going to have the bond breaking between the reactants, and then you're going to have the formation of the product, right? So this transit state is just midpoint of that. So whatever stage costs the highest energy, that point gonna cause that point gonna refer to as transition stage. Okay? So after that, yep.
And those stay where they were, just they didn't break because it's a single bond. Is that how you use?
No, you can break. So here is the thing. That's a good point. So we're gonna see those in chapter 13 and 14. Okay. So it doesn't mean that only rotation you're gonna have. So if you constrain some value, let's say you hit very high temperature, right? Or you pass some electron beams over there. That's gonna break the bond and make ions, fragmentations, other. So that's why, depending on the reaction type, you're gonna have different conditions. Sometimes you're gonna have just rotation. Sometimes you're gonna have the bond breaking and bond making, right? So for bond formation and making, you can see over here. Let's say acid and base. You don't have any rotation over here, right? So what you're gonna do is you're gonna take this out from here and then you're gonna put the other. So you're gonna break the bond over here and then you're gonna form the bond between this and this. So you're gonna have the product over here, like that. You have the bond breaking in the reactant and then bond making to make the product. Okay, so now if you see this type of reaction, then you can do math from different perspectives. Okay, so let's start from the one that we already know. So if you know the acid-base reaction, if you know the pKa, so provided it is a given, for example, okay, so it is given. So this is acid because it's gonna donate the proton donor is acid, right? And then you're gonna have the product on the right side. So this one, this is the conjugate acid given by base, because if you see base, if you compare base and the conjugate acid, what is the difference? So the difference is only one hydrogen, okay? So this part, you have over here this part. Nothing changed on that. The only thing you have is base. So base accepted that hydrogen from acid and then gave the conjugate acid. Why it is acid? Because it can lose that hydrogen and then go back to the base. That's why you have the equilibrium sign there. Okay? So you have two acids there, right? So you have one acid to the right, which is conjugate acid, and then you have another acid to the left, which is initial acid there. Okay, so you have two acids. So if you know the pKa value for these two acids, right, if it is given, then can you calculate the equilibrium constant? So we did that calculation, right? So what do? You take the difference, right? So you're gonna have the difference of pKa of acid to that of conjugate acid. So you're gonna have the difference. So P is just negative log. So pKa is same as minus log Ka, right? So pKeq now it is a difference. So you're gonna have value of that. So you're gonna put the negative log for P and then you're gonna have Keq this value. Right? So before that we used to calculate Keq with simply just the product you have, right? And the reactant you have. That was our equation to calculate it. Equilibrium concentrations, right? But you don't have to do that all the time. So depending on the reaction you have, if it is acid-base reaction, and if you know the pKa value for the acid, you can directly calculate the same equilibrium constant from the pKa balance. Okay? So now here the point is, once you calculate this, can you calculate the other parameters? Delta G, delta H, or enthalpy, entropy, like that. Okay? So now, if you see this equation, delta G, so the KEQ, this is the same value as this one. So if it is a series reaction, if you know KEQ, then you can put that KEQ value in this equation and then you can solve for delta G. Right? So from the equilibrium constant value, you can calculate free energy, this free energy change. Okay? So that's the one you can do. So now once you know that, what about the enthalpy and entropy? Okay, so we can calculate enthalpy, but before that, let's say the entropy, this one. Okay, let's do this, and then we're going to go to delta H after that, right? So what is entropy? How do you define that?
It's a state of
Do you
disorder.
remember the second law of thermodynamics?
It's a state of disorder.
Yes. It is the measure of disorderness in the system. Okay? So if you have the reaction involving gas, you're going to have more disorder in the gas, right? So you're going to have the higher entropy for that. If you have liquid, you're going to have the more order in liquid compared to gas, because the particles are very close together, molecules are very close, or atoms are very close, right? So you're going to have less disorder in liquid compared to gas. You're going to have less entropy for liquid if you compare with the gas. Okay? And solid, you're going to have the least entropy if you compare to solid, liquid, and gas. Okay? So now the question is, if the reaction is given, how to know what value of entropy you're going to have, right? So the simple idea is the disorderness depends on the number, right? If you have more number of particles in the reaction system, you're going to have more ways to be the disordered. Okay? If you have less number, you're going to have the less way to be random. Right? So you can correlate that with the number of particles or number of reactants and products. Okay? So for example, let's see this reaction. So nothing is given over here, but you have the balanced reaction. Okay? So just by counting how many products you have, how many reactants you have, you can guess the change in entropy. You cannot guess the absolute value of entropy. You can guess the change during the reaction. Okay? So count how many products you have. You have one over here, you have one over here. So 1 plus 1, you're going to have 2 products on the right side. Right? And then see the reactant, you're going to have 1 over here, 1 over here. So you're going to have 1 plus 1, that is 2 reactant over here. Right? So you just take the difference of that. So do you have any change in the number? You don't have any change, right? So what is change? Change is going to be 2 minus 2, going to be 0. So 2 product minus 2 reactant. So you have the 0, right? So if you have the 0 change in number, then you will not have any change in entropy. So the change in entropy is going to be 0. So whatever you have the change in number, you're gonna have that change in entropy. If you have product mass reactant 1, then you're gonna have change in entropy 1. If you have 2, you're gonna have 2. That way you can guess just by looking at the reaction. Okay? So count how many you have in the product, count how many you have on the reaction side, take a difference, that's gonna be the change in entropy for that reaction. Okay? So now we know that. So delta S is known for this reaction. Now how to calculate the enthalpy? So the easy way is we're gonna use the equation, this one. You have the change in this free energy, enthalpy, entropy, all three are correlated. Okay? So delta G, we already know from the equilibrium in the previous slide. We know delta G, right? Because delta G equals minus RT ln KEQ, that's the equation in the previous slide. You know KEQ from pKa, then you're going to calculate for delta G, right? So this is known. And then this one from the reaction. Just by seeing the reaction and counting the molecules you have, you know delta S from there. Okay? So now you're going to put the value of delta G, value of delta S, and then you're going to solve for enthalpy. Okay? So see how they are interrelated, right? So entropy gets from the number of molecules in the reaction. And then delta G, the easy way is you're going to calculate KEQ and then calculate that. And then put in the equation, solve, and then you're going to have the delta H like that. Okay? So that's how we going to calculate. So this is what it is shown over here, right? So make sure you review this one. And then after that, we're going to continue. Okay? Good? Yep.